So here's our second example. Again, if you'd like to pause the video so you can copy it down, I'll give you a moment. Okay, so this one talks about a square of cardboard is being used to make an open-topped box by cutting out equal squares from each corner. Find the dimensions that will give you the largest volume. So already I see we talking about largest volume, so ultimately I know that I need to find an equation that describes volume. But first I got to picture what's going on here. And this is the tricky part. Again, if I was with you there, we'd probably give you some time to go off and draw some pictures on the board. And maybe if you want to pause, you could have a little debate in class about what that looks like. But we're going to move on to what the solution is. So a picture is going to be really valuable here. So it says a square piece of cardboard, and the dimensions are 24 by 24, so they're all 24 centimeters, right? So it says we're starting with a square piece of cardboard, and we cut out equal squares from each corner. So again, it doesn't say how big those squares are. Obviously, we don't want to take out like massive squares like this because we'll run out of cardboard. So it's got to be something a little bit smaller, but we're not exactly sure how big, but it's probably something like this. So these are going to get cut out, and it says they're equal squares, so that's important. So when again we don't know how much they are, so we're going to call them little x's. They're squares, so if both sides are x's, so x and x, x and x, and they're all the same. So we have all these equal squares. So now the question is, you can imagine that these get folded up, the corners get folded up, and we get a box with a top on it. So we're going to have to figure out the volume of this box. So I know that volume is the thing we're going to maximize, so it's length times width times height. So I have to imagine what this box will look like with its length, width, and height. So the length and the width are going to be these sides down here, right here, here. They're actually inside here. That's your bottom of the box, because these are going to be gone, and the edges will fold up. So it'll fold up, and this will become a crease, and a crease, and a crease. The red dots are creases. And so those are the bottom, the length and the width of the box. I'm going to imagine that it's going to be the same length and width because it is a square piece. So when we fold up equal corners, it's going to result in the same size. So the question is, how long is this crease along the bottom, or this spot right here? Well, if the whole thing is 24 from here all the way to here, and I take away this little x and this little x from the cutting out, I have 24 minus 2x. And the same on this side over here is going to be 24 minus 2x. So my length and width is going to be 24 minus 2x. Width is also 24 minus 2x. And then all that's left is to consider the height. Well, these flaps that are left over, these flaps here, they get folded up. And that's what makes the edge of the box. And its depth is the height that I'm referring to, and its depth must be x. So the height of the box is actually x. So if you cut out, 5 centimeter squares, you have 24 as the length, and you cut out a 5 and a 5, that means you must have 10 cut out, so 14 left over. And you cut out a little flap that's 5, so that 5 gets folded up, and it's 5 centimeters deep. So that's what I consider the hard part of this. The rest is now finding the largest volume. So what values for x would get us the biggest volume of this box? So I don't know what if it was 5 or 10. Well, it can't be. Well, it could be 10, but maybe it's just a small little corner you take out is 2. You can imagine the different possibilities, but let's ask the math to do it for us. So I need to differentiate this function. I actually have 3 functions here. I can rainbow 2 of them. So I'm going to rainbow the x in here and get 24 minus 2x. 24x minus 2x squared. And I could differentiate at this spot. I could use the product rule by multiplying the derivative of the first times the second plus the derivative of the second times the first. But one of the rules, or one of the things I like to do, is simplify my expressions before I differentiate. So I think it'd be easier if I differentiate, or if I rainbowed again. Actually, I would rainbow the other way. I probably wouldn't rainbow that way. I'd probably go rainbow this way. So let's do that. So 24 times 24 is 576x minus 48x squared. And then the last rainbow here, multiplying by negative 2 is negative 48x squared. And the last one is plus 4x cubed. And just collect like terms gives me 96x squared plus 4x cubed. That's my formula for volume. Now, of course, I'm going to differentiate that and set it equal to 0. I'll give you a moment to get ahead of me. If you want to pause, you could. Do your derivative, set it equal to 0 to solve. I'll differentiate now. So 576x, the derivative of that is just 576, minus 192x, so that's 96 times 2. The 3 comes down and multiplies by the 4 is 12x squared. So that's the derivative, and I know the maximum is going to occur when it equals 0. So 0 equals 576 minus 192x plus 12x squared. So unlike the last example where we just had a linear derivative, this one we have a quadratic derivative. But we still know how to solve these, no problem. We're going to try and simplify and solve as we need to. First thing I'm going to notice, I can make my life a little bit easier dividing everything by 12. So 0 equals 48 minus 16x plus x squared. Now, this is a quadratic. Just for kicks, I'm going to rewrite it the way I'm used to seeing it with the x squared out front. And of course, in this case, we're going to have to factor. Find two numbers and multiply to 48 and add to 16 is negative 12 and negative 4. So this factors to x minus 4 and x minus 12. Each of those will result in 2 answers. This one will result in an answer of 4, and this one will result in an answer of 12. Let's write that later. Okay, so hopefully you had a chance to try each of those to get, or to solve by factoring to get 2 answers in this case, because it's a quadratic, x equals 4 and x equals 12. Now, the question asks us to find the largest volume. We've only found the dimensions here. And I'm going to be critical of my 2 answers. Do both answers make sense? Of course, mathematically, they both are correct. But the second one, of having x equals 12, I'm curious about. If we look back at our picture, the whole thing is 24. If we cut out square boxes of 12 and 12, we would have nothing left over. So if I actually subbed in 12 to figure out the length, it would be 24 minus 2 times 12. That would be 24 minus 24 is 0. So you'd have no length or width. The math is correct because technically we found when it's equal to 0. And it could be equal to 0 when x equals 12 because you would get 0. The volume would be 0. The derivative of the volume would be 0. But in real life, that doesn't make sense. We're not going to use that one. We're going to use the x equals 4 and use those dimensions. So when x equals 4, the length is going to be 24 minus 2 times 4. 24 minus 2 times 4 is 8. And so we get 16 centimeters. So now the volume is going to be length of 16. Of course, the width is also going to be 16. And our height is 4. And that works out to 1,24 centimeters cubed is the maximum volume of this box. You could try it if you wanted. You could cut out, 5 centimeters and do the math to see if that would be less. Let's just do that really quickly in our head. 5 would be, if it was 5, it would be 5 and 5, so it would be 10. So the length in between would be 14. So it would be 14 times 14 times 5. And if we did that number in our head, multiplied that in our head, we would get 980 centimeters cubed. So that box doesn't have as much volume. You could try it with a smaller one like 3. So if you cut out boxes of, or corners of 3 and 3, that's 6. 24 minus 13, there's minus 6 is 18. So it'd be 18 times 18 times 3. And off the top of my head is, and carry the 1, is about 972. So again, not as big a volume. So our math is making sense. It turns out that is the best shape that we have. And it will maximize our volume. So we have had 2 examples. Both of those you need to come up with an equation that you can differentiate to find your maximum and your minimum. That's why we're talking about this being optimization. And once you find that, you differentiate z equals 0, and there's will be your maxes or your mins. So, questions that you can try now. Page 206, number 3, 4, and 14. And depending on what our plans have been, you'll either be reviewing for our quest quiz coming up on this stuff, or you'll be doing an assignment depending on what our plans were this year. Regardless, hopefully this has been helpful, and we'll see you later.